On Friday, when I was doing the review of topics, we kind of ran out of time and didn't get a chance to really talk about eigenvalues and eigenvectors. So I promised that we would start off today getting through those last couple sections on eigenvalues and eigenvectors. And then the one request that I had ahead of time was for a couple of problems from my review problem set. So we will go there next. But let's start by talking eigenvalues and eigenvectors. And let me start by throwing this marker away. Okay, eigenvalues and eigenvectors. So the first thing that is super important in terms of thinking about eigenvalues and eigenvectors is understanding that the fundamental relationship we're always talking about here is that A times my eigenvector is equal to lambda times my eigenvector. So that X there is the eigenvector, and the lambda is the eigenvalue. And what's important about this relationship is, in general, a matrix is a linear transformation that takes one coordinate or one vector and sends it to a different coordinate or different vector. But in particular, if we're talking about looking at the transformation of an eigenvector, then multiplying the matrix by that vector doesn't change the angle of the vector. All it does is change the length or the magnitude of the vector. So that's what's special about this eigenvalue eigenvector pair. Now this equation, if we rearrange it, we can also make that say ax minus lambda x is equal to 0, subtracting that over. And then when we did this, we realized that the dimensions aren't going to work out here. Or rather, the dimensions are fine in this equation, but if I wanted to factor that x out on the right-hand side, I couldn't, because I can't take a matrix and subtract a number from it. So what we do instead is insert the identity matrix, and that allows us to factor the x out so that we're left with a minus lambda I is equal to 0. So this, it turns out, is what's important for us to be able to determine and find the values of lambda, because the only way that this has a solution other than x equals 0 is when the determinant of this new matrix A minus lambda I is equal to 0. So when we find those eigenvalues, and I'm just going to abbreviate that as evals, not to mean that those are your student evaluations or something, but our eigenvaluation, our eigenvalues. When we find those eigenvalues, we're doing that by taking the determinant of A minus lambda I and setting that equal to 0. So let's take a look at a practice problem. So suppose that somewhere here I have a whole bunch of nice ones. Suppose that I had this matrix, let's go with 3, 3, 2, 8. And we were asked to find the eigenvalues and eigenvectors. So in terms of the eigenvalues, we're always reaching back to this equation that the determinant of A minus lambda I needs to be equal to 0. So I am looking for the determinant of, and subtracting that lambda I means I'm subtracting lambda from the primary diagonal. So this will look like 3 minus lambda, 3, 2, and 8 minus lambda. And that's what we're going to set equal to 0. When we do that, finding that determinant, I need minus. So 3 minus lambda times 8 minus lambda minus 2 times 3 is equal to 0. If we distribute this out, that ought to be 24 minus 11 lambda plus lambda squared and minus 6. So if I rearrange that, I'm looking at lambda squared minus 11 lambda plus 18. In general, when we get down to this quadratic point, if it doesn't factor, we're going to have to use quadratic formula. I happen to choose something that's going to factor nicely for us. So I am now looking at lambda minus 9 times lambda minus 2. So I'm going to get lambda equals 9 or 2. So those are my two eigenvalues associated with this matrix. Lambda equals 9, lambda equals 2. Okay, I'm going to erase this because I need the space, but now it's time to talk more about that eigenvector piece. So eigenvectors are never unique. There are always an infinite number of correct answers for your eigenvector. And the reason for that is if we go back to this relationship where A times our eigenvector is equal to lambda times the eigenvector, so multiplying by the matrix A, all it's going to do to that eigenvector is to change the length, which means when we specify an eigenvector, we're really almost thinking about specifying a direction because any vector that lies along that same direction is an eigenvector. So the way that I'm going to go back and find that eigenvector, we could go all the way back to this equation. Typically, Dedel goes back to here. So I'm going to go back to here to find my eigenvectors. So looking back at this equation, my A minus lambda I, let's start with that lambda of 9. So A minus lambda I, or subtracting 9 from my primary diagonal, I'd end up with -6, 3, 2, and -1 times that vector x, and it's okay to write it x1, x2 using subscripts or to write it xy. It really doesn't matter. I'm going to go with xy. My next step, if I do the matrix multiplication on this side, we're expecting to get two equations that are giving us the same piece of information. So if I were to multiply this out, that looks like -6x plus 3y equals 0 for the top row. And on the second row, I'd have 2x minus y equals 0. Now these two should be giving us the same information. If I take that bottom equation and I multiply by -3, I get the top equation. So it doesn't matter which one we work with. I'm going to choose the bottom equation just because the numbers are smaller. So if I think about this bottom equation, really, if I'm like going for any possible eigenvector, this is the equation of what's sometimes referred to as the eigenline, and that's something we're going to work with in 17C. So this relationship tells me that any point that lies on the line y equals 2x any point on that line will represent an eigenvector. In general, we can choose any point on that line, and there's a subtlety in the way that the question might be asked. So if I ask you to find an eigenvector, you know, I'm giving it a definite article, I'm asking you to find a definite eigenvector, then you can make any choice you want for x and y values. But if I ask you to find the eigenvectors, or ask you to find all eigenvectors, that's when we want to be careful to use the notation with a T in it. And that notation is not in our textbook, but it's not in our textbook for 17B. It will be in our textbook for 17C. So I think Dedel's just kind of getting a jump start on that. And it definitely was notation in our previous textbook. So if I go back to this, the way that that T notation works, and for the sake of you have a final exam tomorrow, I would say in this moment, just pick. You're always going to set X equal to T. You can choose either one, but at this point, studying for your final exam, let's just go with here's a method that'll work every time. So once you're down here to your two equations, I'm going to take the X and replace it with T. So if I replace my X with T, then Y would be 2T. So if I think about that as a vector pair, as my X, Y vector pair, X is equal to T because we called it T, and Y is equal to 2T. So any vector that has this form is an eigenvector. We could choose to plug in 1 for T, and that is always the solution that our textbook gives. So if you're working on problems from the book and trying to check your work, the book always simply chooses to plug in 1. So in terms of writing my solution, I would, if I call this lambda 1, then I would say that my x1 vector looks like, and I'm going to take this but factor the t out. So it's going to look like 1, 2 with a t on the outside. Now we're going to repeat that process, but for a lambda of 2. And I'm going to leave this picture up here for a second. Yeah, let me get rid of the rest of this. So now, if I'm subtracting 2 from the primary diagonal, then 3 minus 2, I get 1, and 8 minus 2, I get 6. So multiplying that out, I get x plus 3y is equal to 0, or 2x plus 6y is equal to 0. Again, these two should be giving us the same piece of information. If they're not, you made a mistake with your eigenvalue. So if I take the top row and I multiply by 2, I get the bottom row. This time, the one I'm going to work with is the top row because the numbers are smaller. That's my personal choice. So I'm not going to worry about the second row. I'm going to worry about the top row. And if we're going to follow that same technique of I'm going to replace x with t, then this equation, if I rearrange it, or actually if I rearrange it even before plugging in the t, this would look like y is equal to negative 1/3 x. So if I were thinking about what that eigenline looks like, now that is something like this. So for a lambda of 2, any point on this line is an eigenvector. So back to this, if I replace the x with t, then my x2 vector would look like, well, we replaced the x with t, so I'll have t on the top, and then I'll have negative 1/3 t down here for the y value. So I could write that as 1 negative 1/3 t. Just a quick recap. I'm going to find my eigenvalues always by looking at the determinant of a minus lambda I. Once I've got those eigenvalues, I'm plugging them back in to this equation right here to solve for my eigenvectors. Eigenvectors are not unique. It's never a specific eigenvector that's your answer. Really what we're finding is a relationship between x and y for the eigenvector. So once you get that relationship, then any point along that line is an eigenvector. And notation-wise, Dedel prefers for us to write it like this with a t so that we're expressing all possible eigenvectors. Now there's a catch. When you are doing the problems where, I'm going to erase this for a second. So we want to be able to write those eigenvectors generically with the t in them. However, If we are asked to express A in the form of PDP inverse, meaning to diagonalize A, or if we are going to represent A to the K power times a vector, and I'll just call it N naught to be consistent with the textbook notation, that N naught vector as C1 lambda 1 to the K x1 plus C2 lambda 2 to the K times x2. If you are working with either of these two formulas, and those are both from 8.8, you must choose a value for T. So for example, if I was asked to diagonalize this matrix or write it in the form of PDP inverse, I would have to choose specific values for T to work it out. So in that case, the textbook will always choose a T value of 1. You do not have to choose the same T value for the two eigenvectors. I always choose a T value that means I don't work with fractions. That's just my preference. So let's go ahead and do this for this guy right here. We don't really need any of this because we've already worked out our eigenvectors and eigenvalues. So let's say that I was asked to diagonalize this matrix or to write it in diagonal form. That means we're looking to do this. So to form that P matrix, I need to choose particular eigenvectors. So for this, I'm going to let T be equal to 1 and say that my x1 is a vector 1, 2. But for my x2, I want whole numbers. So I'm going to choose T to be 3. And that's going to give me a vector of 3, negative 1. Now that I've got my two eigenvectors set, and again, it does not matter which vector you choose. And you do not have to choose the same T for both of the vectors. So now I can write it in this form. So my P is going to be the matrix formed by my two eigenvectors, 1, 2, 3, negative 1. D is the matrix of my eigenvalues, and they have to go in the same order. So if 1, 2 is in that first column, then I need to put 9 in the first column for that eigenvalue. So that's going to look like 9, 0, 0, 2. And then our last P is P inverse. Well, we need to find P inverse. So if this is P, then I know for my inverse, I'm going to need the determinant of P. So that is 1 times negative 1 minus 2 times 3. So that's negative 1 minus 6, or negative 7. So my P inverse, I'm going to be dividing all of the terms by negative 7. To get the inverse, I swap that primary diagonal. So I'll have negative 1 divided by negative 7 and 1 divided by negative 7. And then I change the sign on the off diagonal. So I'd have negative 3, negative 2. So if you had chosen to plug in different numbers for T, your P and P inverse would be different matrices, but it's okay. It would still be a correct answer as long as you chose eigenvectors of the original matrix. Now, along those same lines, suppose that we weren't asked to do the PDP inverse thing, and instead we were asked to find A to the 5th power times the vector, I don't know, 5, 3. Oh, hold on. The chat was scrolling a little too fast and I missed a question. Got it. I think my question got answered. Okay, yes. So for The determinant as a number is just the value that you get when, for a 2 by 2 matrix, you do the diagonal multiplied minus the off diagonal multiplied, but the formula for P inverse includes 1 divided by the determinant. So that's why I was dividing by the -7, but I did forget to divide by -7 on the off diagonal. So thank you for catching that. Yes, I should have divided by the -7 in the entire matrix for P inverse. Thanks. Okay, so back to here. If I had to compute a to the 5th times the vector 5, 3, this is where we're using that formula, which is going to look like C1 lambda 1 to the 5th times x1 plus C2 lambda 2 to the 5th times x2. And again, if we're using this formula, it is important that we work with actual eigenvectors, not the ones that have the t's in them. So I'm going to use these same 2 vectors for x1 and x2. So that means this is going to look like, I'm going to hold off on putting the C1 in for just a second, but I'm going to have lambda 1, so that's going to be 9 to the 5th times my vector 1, 2. We'll leave a little space for C2. Lambda 2 is going to be 2 to the 5th, and we'll have 3, -1. And now we need to solve for C1 and C2. So your choice of these eigenvectors will determine what values you end up with for C1 and C2. So if you're like working through textbook problems, or you're trying to follow one of Kuba or Didel's practice problems, if you don't choose the same eigenvectors, you won't get the same constants, but you'll still be correct. Because if you think about it, if you were to simplify this, you'd end up multiplying the constant in times the values of the vector. So that's where you would be able to compare, as long as your constant times your vector worked out to be the same thing as his constant times his vector. Okay, so to solve for the C1 and C2, there are 2 ways to do that. The textbook version uses P inverse. I just hate that because I don't like fractions. But so to solve for the C1 and C2, really what we're saying is that this vector 5, 3, we're trying to write that as C1 times our first eigenvector plus C2 times our second eigenvector. The other way to phrase that is we're writing 5, 3 as a linear combination of the eigenvectors. So we can turn this into a matrix form and then multiply 5/3 by P inverse. I'm just going to write this out as 2 equations and solve it. So that says 5 should be equal to C1 plus 3C2, and 3 should be equal to 2C1 minus C2. So this is 2 equations and 2 unknowns. One of our methods for solving a system like this is to use elimination. So if I were to take that top row and multiply all of the terms by -2, that it would make the C1 terms go away. So I'd have -2 times 5 and get -10 plus 3, so that's -7. My C1 terms would go away because I'd have -2C1 plus a C1. And then I'm going to have -6C2 minus another C2, or -7C2, which means C2 is equal to 1. And if I know that C2 is equal to 1, then it's pretty quick to find C1. So if C2 is equal to 1, and I think about plugging that in here, adding it to the other side, I'd end up with 4 is equal to 2C1, or C1 must be equal to 2. on last Wednesday, so on your last day of class, Didel did say that you would not be expected to simplify this out. And there's a question in the chat about whether you would have to multiply this out. I would say no, unless specifically the word verify is part of the problem. So if I asked you to verify that this diagonalization is equal to A, then you would be expected to do the multiplication. Question about how I got the C1. So once I know that C2 is equal to 1, then you could plug it into either of these equations to get the C1. I happen to plug it into the second equation here. So I had 3 is equal to 2C1 minus 1, and then moved it over to the other side. Yeah, but in terms of simplification, I know that Didel specifically addressed this and said you would not need to simplify this anymore, and you wouldn't need to simplify this, again, unless that word of verify was part of the question. So if it said to verify this is a diagonalization, then you would need to multiply it out to show that you get back the original A matrix. Okay. I'm not seeing any more questions bubble up in the chat. So I think I'm gonna move on to take a look at a couple questions that were submitted ahead of time. And feel free to add more questions to the chat as we go here. So I got asked a question ahead of time about my review problems, and I totally missed this. I managed to catch them on Kuba's test and tell you not to do the ones that involve Taylor polynomials. In the old textbook, Taylor polynomials were in 17B. In our current textbook, it's in 17A. So you already did Taylor polynomials. You're not getting tested on that for your 17B final. So you don't have to worry about the Taylor polynomial questions. Hopefully that was already on your final from 17A. But I will take a look at problem 19 from my practice review problems. Okay, so problem 19 on my review problems has 2 radically different and unrelated questions. So let's just start with the first question, which says y prime is equal to -3 t squared y plus t squared, and we've been given the initial condition that y of 0 is equal to -4. Well, if I'm asking you to solve this differential equation, we've only got 2 methods for solving in 17B. So either it's first order linear, or it's separable, or it's both. I always start by checking if it's first order linear, because this one doesn't require me to magically view algebra skills. And just to make sure, in case somebody has to run off, I will post this to the YouTube playlist, and I can also throw it on Canvas. I'll put it everywhere, the video from today. And I'm not going to try to edit it at all. I'm just going to put it up there to make sure that you have it faster. Okay, so back to this. It is first order linear. It's first order because I just have a y prime, not a y double prime anywhere. And since y is my variable of interest, the only other place y shows up, there's an invisible exponent of 1. So it is first order linear. It also happens to be separable. And in general, if I can separate it, that's my preference for how to solve it. The reason that I can look at that and see that it's separable is, in order to be separable, am hoping that this side factors. If this says y prime equals or x prime equals or n prime equals, and I can get this side to factor, there's a good chance that it's separable. In this case, I can pull out that t squared, and I can make this t squared times negative 3y plus 1. Now, it's not enough that this side factors in order for it to be separable. It has to factor and isolate my two variables, meaning this factor only contains y and this factor only contains t. So now I know it's separable. I'm going to go ahead and rewrite that y prime to say dy dt. When I do that, we now do not get a choice of which side of the equation the y's go on and t's go on. We can't integrate something with a 1 over dt or a 1 over dy. So my only option is to multiply both sides by dt, which means my t's should be on the right and my y's should be on the left. So I'm going to divide this over and have 1 over negative 3y plus 1 dy is equal to t squared dt. Now that we've separated this, we can go ahead and integrate. I've kind of been pushing hard on this all quarter in terms of it's just a linear term at the bottom. So I know that when I find the antiderivative, I'm going to end up with natural log of all of that in an absolute value, and I'm going to need to divide by negative 3 to counteract what will happen with the chain rule if we take the derivative of this result. If that's still making you uncomfortable at this point, that's okay. Just take a minute to write out the u substitution. So if you were to let u be equal to negative 3y plus 1, that negative 3 would pop out as a part of your du in the u sub. On the right-hand side, if I integrate t squared, I'm going to get t cubed over 3 plus a constant. Now, in general, it might be okay to just quit there, but there are two factors working against us. I know we've got to solve for c, and if I'm looking at this, it's not too bad to get the y by itself. So we should probably go ahead and do that. For my sake, when I look at this, I don't really want to mess around with fractions, so I would choose to multiply the entire equation by negative 3. If I multiply everything by negative 3, then I get ln absolute value negative 3y plus 1 is equal to negative t cubed, and negative 3 times this constant is still a constant, so I'm just going to call it c2. And when I get down to the end, and I'm sure I'm not going to mess with any more constants, that's when I'll go ahead and write it as a c. To get rid of my natural log, I'm going to raise both sides to the e, and I'm going to end up with absolute value of negative 3y plus 1 is equal to e to the negative t cubed plus that constant. But I can take that constant. Remember, because I've got addition in the exponent, that's the same as writing it as e to the negative t cubed times e to the c2. We'll go ahead and just call that a new constant. So with a constant out in front, I no longer need the absolute value, because with that absolute value, it's either telling us that negative 3y plus 1 is equal to the positive this, or negative 3y plus 1 is equal to the negative this. But that plus or minus piece is going to be taken care of with our constant, especially since we've got an initial condition. We'll be able to figure out whether that constant should be positive or negative. So rewriting that up here, I'm at negative 3y plus 1 is equal to c e to the negative t cubed. So y is going to be c e to the negative t cubed minus a 1, and then the whole thing is divided by negative 3. Or, I may have gone too soon, assuming I was at my final constant. I'm going to go back and call that c3. Because if I split this into two pieces, then C3 over -3 is some constant. And a minus over a minus is going to make that plus 1/3. So this is the general solution for the differential equation. And I'm going to use that initial condition to find the particular solution. So looking at this notation-wise, this tells me that t equals 0 and y equals 4. So if I set y equal to 4 and t equal to 0, then e to the 0 is 1. Just sneak a little over there. So it looks like 4 minus 1/3 is going to give me c. So I'll just go ahead and change that 4 to, I don't know what I'm trying to write. I'm going to change that 4 to a 12/3 so that I have a common denominator. So if I multiply that by 3 over 3, then I'll have 12/3. Subtracting 1, that's going to be 11/3 is equal to my constant. So the final answer is me taking that 11/3 and plugging it into the general solution. Okay. If we had done this as a first order linear differential equation, we should have gotten down to exactly the same answer in the end. It just would have been a different set of work that we did together. And it wouldn't matter in terms of the exam, you would get all of the points either way, unless the question specifically told you to use the first order linear method. Or it's sometimes also referred to as the integrating factors method. Okay, I'm going to move on to part B of the same question. So part B says, a spherical cell has a volume V and surface area S. A simple model for cell growth before mitosis assumes that the rate at which the cell grows is directly proportional to the surface area of the cell. So I gave us the differential equation in this problem, but I didn't necessarily have to. So I do want to walk through this kind of the long way. So putting that in words, that says the rate at which the rate at which a cell grows is proportional to the surface area. So if that was all of the information that we were given, we would be able to still write the differential equation. So the rate at which the cell grows, that is telling us dV dt. So growth meaning how much is the volume changing. So that's the rate at which it's growing. Is proportional to always means equals. That's where my is goes. And the proportional to means I need a constant. Now, if this is proportional to the surface area, I'm just going to put an S in here for a second. Now, the problem is this differential equation actually has a constant and 3 variables in it. So I wouldn't be able to solve it using any of the methods that we have so far. However, I can use my algebra skills to rewrite the surface area in terms of the volume. Now, I don't think that's reasonable to ask you to do on a final exam, but this could have been a fun homework problem. In fact, I pulled it out of the textbook. So in the homework problem, it wasn't one that Dedell assigned, but in the problem in the textbook, you first had to write the surface area in terms of volume. So I'm going to cheat and skip to the answer because I gave you the answer on the practice final, which is the surface area is equal to the volume raised to the 2/3 power. So in terms of the question I asked, we really just started here. If dv dt is equal to a constant times v to the 2/3, find a general solution for v. And again, that phrase general solution means we're still going to have a c in our final answer. This is not first order linear. It is first order, but it's not linear because v is raised to the 2/3 power. Luckily, it is separable. So that dv dt side tells me my v's have to be on the left and my t is going to the right. So if I divide that v over, that's the same as writing it as v to the negative 2/3 is equal to k dt. Now I'm ready to integrate both sides. So on the left-hand side, this is an algebra problem raised to a power, so I know I'm going to add 1 to the exponent, so I'll be at v to the 1/3, and then divide by the new exponent. But dividing by 1/3 is the same as multiplying by 3. On the right-hand side, I'm going to get k times t plus a constant. So in this case, I'm actually going to end up with 2 constants in my final answer. In terms of the general solution, I know I'm trying to get v by itself. Because I'm not going to have to solve for the constant at the end of this, because all I was asked to do is find the general solution, I'm not going to do anything to simplify the constants in this. I'm just going to take v to the 1/3 power is equal to kt divided by c, or sorry, kt plus c divided by 3, and then raise both sides to the 3rd power. So we'll just cube this and walk away right there. In terms of simplifying constants, k, that constant of proportionality, that one we can't simplify with the 3. We could only have simplified this c with the 3, because essentially that k was set even before we did the problem. It's some kind of parameter that we weren't given in the problem, but it's already fixed. Whereas this constant, that's a constant that was the result of our doing the integration. So this one, we could say that c over 3 is just some new c value. Okay. So we have now hit all of the questions that people had sent me ahead of time. Are there any particular questions or topics that anybody wants me to spend a little bit more time on right now, or should I pick some things? So I'll give it a minute in the chat. I'll drink a little bit more of my coffee and stare at you awkwardly. No. I'll turn my back on you awkwardly. That's way more awkward. But if you have any questions that you want to add to the chat, now would be a great time. And I will so let me ask you this. Has everyone finished all of the problems on Didel's test 3 practice? The problems he posted? Are there any questions from Didel's practice 3 that folks that we haven't gone over yet that anybody got stuck on? Because I would say of all the things, that's definitely one you should make sure you're totally good with. The other thing is, so half of the points on the final are coming from new stuff, but that also means that the other half is coming from old stuff. So don't neglect the old stuff. So I am right now pulling up I'm trying to pull up midterm 1 solutions. Just to check. Are there any questions from Didel's first midterm that anyone would like to go over at this point? Okay, since no one has questions, I'm bringing the questions. Oh, okay. Number 3 on the 3rd practice test, sure. And I assume we're talking about Didel's practice problems. So number 3, we have been given 2 vectors, u, which is the vector 2, 6, b, and v, which is the vector b, b squared, b. And the first part of the question is, or this is part A of the question, and we are asked for what values of b are these 2 vectors orthogonal. Well, orthogonal always means perpendicular, and that means that our dot product needs to be 0. So b dotted with u has to be equal to 0. So if I start to take that dot product, I'm going to have 2 times b plus 6 times b squared plus b times b. Well, that's not going to leave a particularly pretty equation, but it factors. So I'm looking at 0 is equal to 2b plus 7b squared. We can factor a b out and then have 2 plus 7b. So it looks like if b is equal to 0, now if b is equal to 0 and we look at the vector b, that would lead us to the trivial solution. So the 0 vector is orthogonal to everything because when you do the dot product, it will be 0. The more interesting solution here is that b is equal to -2 sevenths. So that's the value of b that would make these 2 orthogonal. The second part, we're asked to find 2 unit vectors that make an angle of 60 degrees with v, which is equal to with this vector here. And we actually did that question at some point in time last week. Happy to do it again. The algebra gets messy, so we can definitely do this. Just know that the algebra gets messy, so it's not going to be quick. I'm going to erase this though. So we've been given a vector v, which is 3 to the right of 4. So we have been given this vector v, and v is 3, 4. And we have been asked to find 2 vectors that are unit vectors, meaning have a length of 1, that make an angle of 60 degrees with this vector v. So we're going to have some vector over here that's 60 degrees off, and some vector over here that's 60 degrees off, and we're trying to find those 2 vectors. If the only thing that we know is that they're 60 degrees apart, I'm just going to go ahead and call this vector A and work with the fact that we know it's 60 degrees. So if I think about my vector A as something generically x comma y, then the fact that it's a unit vector means the length is 1. So the square root of x squared plus y squared must be equal to 1, which also means that x squared plus y squared must be equal to 1. Working with that angle of 60 degrees, that means that we're going to use the dot product equation that looks like u dotted with v is equal to the magnitude of u times the magnitude of v times cosine of the angle between them. So in this case, I'll just turn my u's into a's. So a dotted with v is going to look like 3x plus 4y. Now the magnitude of a, because it's a unit vector, this is just going to be 1. And the magnitude of v, we're going to find by doing the square root of 3 squared plus 4 squared. 3 squared is 9, 4 squared is 16. Add those together, I've got 25 under the square root, or a value of 5. So now I've got 1 times 5 times cosine of 60 degrees. Quick recap, if I'm looking for cosine of 60 degrees, I'm thinking about this equilateral triangle. That side's 2, that side's 1, and that vertical side is the square root of 3. There's my 60 degrees right in there. So cosine of 60 degrees is 1/2. So I'm going to replace cosine of 60 with 1/2. So I will have 3x plus 4y is equal to 1 times 5 times 1/2, or 5 halves. I could also multiply that 2 over and say 6x plus 8y is equal to 5. Now at this point, that's just an equation, but we were trying to actually find the values of x and y. Good news is we now have 2 equations with 2 unknowns. That first one came from knowing that a was a unit vector, and we just got that second one from the relationship of the 60 degrees. So when we solve these 2 equations simultaneously, we can get values for x and y. What that looks like algebra-wise is taking this equation and either making it say x equals or making it say y equals. It doesn't matter which one. They're both messy. I'm going to arbitrarily choose to make this say y equals. So I would say 8y is equal to 5 minus 6x, or y is equal to 5 minus 6x divided by 8. And that's the equation that I'm going to plug in over here for y. I am not going to finish this whole thing off. I'm just going to get us as far as saying this turns into x squared plus 5 minus 6x over 8 whole thing squared is equal to 1. The fact that this was an assigned homework question, and then he also put it on the practice problems. So actually, I don't know if you noticed, but a lot of the practice problems are coming directly from homework questions. So just be thinking about that reviewing the problems he assigned for homework is another way that you can be studying between now and tomorrow. So anyway, from here, you'd have to multiply this out, and then it won't be nice. You have to use quadratic formula. In his homework solutions, when he did this problem, he made a mistake and switched the x and y values. I don't recall, I don't recall whether in the solutions for this, he swapped the x and y values, but he definitely did in the homework solutions for this problem. Okay. That's it. I'm walking away from this one. It is quadratic. It's messy. You're going to use quadratic formula. You're going to get terrible numbers. Now I bet he could write, so Tidell's super clever and he is often able to write questions for an exam where the numbers do magically work out much nicer. And so it wouldn't surprise me if he found one of these problems, but where this worked out to something a little bit better. I'm not saying that you wouldn't have to use quadratic formula, but maybe something where it just simplified a little bit. Are there other questions that people have that they would like to go over right now? My thought was to go back to some older things and to practice just taking some integrals, using our different methods of integration to review those, do some problems. And since I'm not seeing any other questions, I'm not seeing questions pop up. So let's go practice some integration. And I will keep an eye on the chat. So even though I'm picking some problems for us to do, if you throw something in the chat, we will definitely do those. Okay. So looking at this problem, if I walk up to it, I'm asking myself, is it algebra, trig, or a mixture of stuff? It's just algebra. So now I'm running through my algebra methods. Well, it's a fraction. Since it's a fraction, I should check, is the power on top greater than or equal to the power on the bottom? It's not. So I don't need to do long division. Now I'm going to look at the bottom and ask myself, does it factor? And the answer to that is yes, it does factor. So I know that I can do partial fractions. But even before I start, I'm going to do a quick check to make sure it's not secretly a U substitution. So if this were going to be a U substitution, U would be the denominator. And if I take the derivative, I'd end up with 2x plus 1. That's really not what I have on the top, and there's no way to manipulate the top to be that. So it's not a U substitution. We're going to move into partial fractions. So I'm going to come off to the side and say 1 minus x over x squared plus x. And thinking about the denominator, I said it factored, but I didn't actually factor it. So let's pull that x out and have an x plus 1. So I know I'll have something over x plus something over x plus 1. When we get to this point, I'm going to take both sides of the equation and multiply by the common denominator. So I'm going to multiply by x times x plus 1. On the left-hand side, that means we're left only with the numerator. And on the right-hand side, for each piece, one factor is going to cancel out and the other won't. So I'm going to have a times x plus 1 plus b times x. This is where we have two different methods where we can solve. We can either multiply out the right-hand side and match up the coefficients, or we can choose nice numbers to plug in for x. I'm a fan of plugging numbers in. So my nice numbers here would be x equals -1 or x equals 0. Well, if I plug in -1, 1 minus -1 would be 2. That'll be a times 0, and I'll get -b. And when we plug in 0, I'll have 1 is equal to a times 0 plus 1 plus b times 0. So that top equation is telling me that b must be -2. And the bottom equation is saying that a is going to be 1. So that means instead of the original integral, we are going to integrate a 1 over x plus, or let me make that a minus since it was a -2. So I'll make that minus 2 over x plus 1 dx. So I'm looking at natural log of x minus 2 natural log of x plus 1 plus a constant. Little quick partial fractions there. Still not seeing any questions pop up in the chat, so I am going to keep picking problems. So I'm going to do another random integral, and then maybe we can practice setting up some area and volume stuff. Okay, so 2 things. I have given us limits of integration, and one of those limits has an infinity in it. So I know that we're going to have to integrate this thing, but we'll also have to address the fact that it's an improper integral. I'm going to deal with the improper integral first. So I'm going to replace that infinity up top and instead write this as a limit. So I'm going to take the limit as b approaches infinity. Oh, and then I rewrote the infinity. I'm going to take the limit as b approaches infinity and throw a b up on top. Now I can take a step back and look at the integral. So I'm asking myself, is it algebra, trig, or a mixture of stuff? It's a mixture problem the moment I've got exponentials in it. So I'm personally always hoping for a u substitution. And it turns out we have one. We just have to be clever about that e to the 2x in the denominator. Oftentimes when we're taking integrals, we want to think about e to the 2x as actually saying e to the x squared. So that e to the x squared piece means that I can set the entire bottom to be u. Or rather, I can set that e to the x to be u. So if u is equal to e to the x, then that's going to make du e to the x dx, which I have. I have that e to the x dx. We're going to pause for a second here because when we do this u substitution, that's also going to affect my limits of integration. So instead of going from 0 to b, I need to think about what's happening in the original, or rather with our u substitution. When x is equal to 0, u would be e to the 0 or 1. And we have a choice. We can either deal with our limit now, or we can say when x is equal to, no, I lied, this is the better option. When x is equal to b, that means u is equal to e to the b. It's a little bit cumbersome to rewrite it that way, but it's the most mathematically precise option. So I'm going to say the limit as b approaches infinity, we're now going from 1 to e to the b. And that e to the x dx, that turned into du. So I'll have 1 over 4 plus u squared du. We talked about this a while ago, but our book actually gives the most generalized formula for arctan to be the integral of 1 over a squared plus u squared du. And when we have that a squared in there, and I'm just double checking the formula in the book, making sure that I don't get it wrong. Of course, I thought I knew exactly where it was in the book and it wasn't there. It's okay. I'm gonna grab a different book. So when we have a constant squared plus u squared in the denominator, then rather than just being arctan of x, it's 1 over that constant, arctan of u over that constant, plus c. Which means if we have this formula memorized, which clearly I didn't, but I promised before that first midterm I did, I've just forgotten it at this point. If we had this formula memorized, then we could go straight from here to, oh wait, we're gonna pause momentarily. And I'm gonna say something about memorizing things. So we're taking that limit, we're gonna get 1 over 2 arctan of u over 2 from u equals 1 to u equals e to the b. And plugging in our limits, that's the limit as b approaches infinity of 1/2 tan inverse of 1/2. Oh wait, top minus bottom, plug in the top first. E to the b over 2 minus 1/2 tan inverse of 1/2. If I take this limit as b approaches infinity, e to the infinity is going to infinity, and infinity over 2 is still infinite, and tan inverse of positive infinity is going to pi over 2. So this looks like 1/2 times pi over 2 minus 1/2 tan inverse of 1/2. Well, I don't know what that is, but it's a number. So this definitely converges. We did not get something infinite. So back to this formula piece. I'm not used to final exams or midterms or anything being open book, open notes. So it has occurred to me that if you haven't already done this, you should bookmark section 5.7 of, I think it's 5.7 of our textbook that has the integration tables in it. Sorry, I'm trying to get you a page number really quick. You might even, like if you have the E version of the book, you might want to print it out. This particular formula is on page 372 of our textbook, but there is, it keeps saying, oh, I got it. It's in the table of integrals. It's on the reference pages 6 through 10 at the front of the book. So if you have the physical book, there's like that stack of stuff at the front that's kind of cardstocky that has tables of integrals. Since this is open book, I would definitely like have those neatly on hand, because this is totally a problem where if you didn't use this formula, you can still integrate this, but you've got to do a lot more work to make this into something nice. And using the table of integrals definitely goes faster. So since it's open book, I would, if you use this, probably say from the table of integrals, right? So that you're being really clear to your TA. I got this out of the book. This test was open book, open notes. So this is for sure one that you should do. And this one, again, that particular one is on page 372. Okay. So weird to be open book, open notes. We've got about 45-ish minutes left. I'm still not seeing any questions pop up in the chat of problems that people wanted to take a look at. So I'm just going to keep working through more problems. So let's consider a region. Bounded by y equals 6 minus 3x, y equals 0, and x equals 0. And then we're going to find the volume of the solid if cross sections perpendicular to the x-axis are squares. Okay, so I'm probably going to start this one by taking a look at a picture of our region. Y equals 6 minus 3x, that is a line with an intercept of 6 and a negative slope. And we want bounded by x-axis, y-axis here. So that's the triangular region we're talking about. If we're finding a volume, we know that Didel has said there will be one volume question on the test, and it will either be a volume with cross sections perpendicular to an axis, or it will be a volume of rotation. So we're going to start here with the cross sections. So if my cross sections are perpendicular to the x-axis, then on my picture, I'm going to go ahead and draw in that arbitrary thing. Now we've established that I don't draw well in 3 dimensions, and I don't need to, but sure, that's a square. Yes. So this square is sticking out from the board perpendicular to the board. So this square has one edge that's drawn right there. Or to kind of come off to the side to draw it, we're going to have this square with a little bit of thickness. And that little bit of thickness is going to be the dx. In general, when we're finding area, or sorry, when we're finding volume, my volume is going to look like my cross-sectional area times the thickness. And this holds even if we're doing rotation. It's just that if we're doing rotation, that cross-sectional area is always a circle. Well, in this case, it's been specified to be a square. So that cross-sectional area, we need a formula for the area of that square. Well, this side, I'm going to call y. which means that this area would be y times y, or y squared, because it's a square, and our thickness is dx. Well, that's not going to work out for us as an integral. I can't integrate my y's with respect to x, but we do have a formula for what y equals. So rather than writing it as y, I'm going to put in 6 minus 3x squared dx. Now the next piece we have to figure out is where our cross sections are so that we have our bounds for the integral. So these cross sections, they're going to come as far to the left as 0, as x equals 0, and as far to the right as, okay, we're going to need to know that point there. Well, if that's the line 6 minus 3x, then I know that has an intercept over here at 2. So we'd be integrating from 0 to 2. And Didel has said that for the, does anyone remember? I'm pretty sure that what he said is that the area question would be a setup only, but the volume question we might have to actually calculate. Let's be prepared to calculate it. If you only have to do the setup, then we're done right there. But if we have to calculate it, let's just take it one more step. Now, if I'm going to calculate it, we have two choices. I can either deal with this as a U substitution or multiply it out. Because I'm kind of short on chalkboard space, I'm going to choose U substitution. If I let U be equal to 6 minus 3x, then du is negative 3 dx, meaning negative 1/3 du is equal to dx. So I know this I can change to negative 1/3 u squared du. But I have to deal with the limits of integration. So when x is, and I have to keep them in the same order that they were originally, since the 0 is on the bottom. When I plug in 0 for x, I'm going to get 6, but that has to stay on the bottom. So I'm going to put my 6 down here. 2, when I plug in 2 for x, I get 0, but because the 2 is on top, my 0 is going to have to go on the top as well. And we can use one of our properties of integrals and take that minus sign and get rid of it by switching the order of my limits. So this is equivalent to saying 1/3 from 0 to 6 of u squared du. You don't have to make that switch, but it's an option that you can do. Well, if I integrate u squared, I'm going to get u cubed over 3. And since I already have that 1/3, it's going to be 1/9 of u cubed from 0 to 6. And for sure, I don't know what, maybe I do know what 6 cubed is, but certainly in a final exam when I'm rushing, I wouldn't worry about figuring out what 6 cubed is. So my final answer would look like 1/9 of 6 cubed. And I would just leave it right there. Could we simplify it? Yes. And if you're quick with numbers, for sure, simplify it. Okay, so that was us finding the volume of a solid with cross sections that are squares. Let's go back now and find the volume of the solid if we revolve around something. Checking for questions, not seeing any questions in the chat. So I'm going to go ahead and erase this. Oh, I'm going to leave my picture up. Okay. So I want to find the volume formed if we take this and revolve it around x equals 2. Well, thinking about my picture, I'm going to get rid of this cross section because that belonged to the one where we were perpendicular to the x-axis. So I'm going to get rid of that cross section, come back to my picture here, and instead draw in our axis of rotation, which is the line x equals 2. Well, if I take that shape and I spin it around x equals 2, since this is a volume of revolution, I know that my cross section should be perpendicular to what we were spinning around. Now, some of you have taken calculus in a previous life, or you're watching videos out there on the internet. There is another method called shell method that our textbook does not discuss. So in the context of 17B, if I'm doing a revolution problem, my cross section should always be perpendicular to the axis of rotation. I'm revolving around x equals 2, so I've got to be doing a dy. Now looking at that, I'm revolving around something that doesn't touch my shape everywhere, right? If I were revolving around the y-axis, then no matter where I was on the axis, my shape would be touching the y-axis. That's not the case here, which means when we go to set up the volume, I know we're going to end up with a pi big R squared dy minus the pi little r squared dy for our integrals. Let's deal with our bounds for the integral first. These cross-sectional slices, they're going to come down as far as 0 and up as far as 6. So my integrals are going to go from 0 to 6. I'm going to have something squared dy and pi, and then 0 to 6, and something else squared dy. Now I'm looking for my inside radius, outside radius, or big radius, little radius. Let's do the little one first. So if I start at my axis of rotation and I come out until I hit that cross section, then that's going to be my little radius. I know that this entire distance here is 2, but if we think about the function and where that cross section is, that distance out is the x value. So to get my little radius, I'm looking at 2 minus x. Oops, that was my smaller radius. To get the larger radius, well, it turns out that everywhere in my shape, my outer radius is 2, because this edge of the shape is always a distance of 2 from the axis of rotation. I'm going to have the same problem this time that I did on the previous question, which is I can't integrate something with x's with respect to y. So I'm going to have to go back to the original equation and rearrange that to make it say x equals. Here, looking at pi times the integral from 0 to 6 of 2 squared dy minus pi times the integral from 0 to 6 of 2 minus, if I come up here and I rearrange this for x, 6 minus y over 3. So this would be our answer if we were to set up the volume. Now to actually finish that off, I'm not going to worry about right now, but to actually finish it off in here, I might get a common denominator and then square it, just so that I'm not having to multiply this times itself again and FOIL that out. Still not seeing any questions in the chat, so I assume that means the problems I'm picking are okay. So we've got 30 minutes left. I'm going to keep picking more problems. And you can stop me at any time and throw a question into the chat. let's see, what other fun things? We've done some volume, some area, we've done some differential equations. We haven't done any Euler's method or stability problems today, so let's pick some differential equations. Oh, you know what? I've got a good question for us. Hold that thought. So I'm actually going to take a look at a question from my practice problems, but I know that I only provided an answer to question 28, part B, but let's actually talk about why. So let's say that I know that dc dt is equal to k times 4 minus c times 10 minus c, and then what I want to do is say for what values of k will c equal to 10 be a stable equilibrium. Okay. So first of all, looking at that equation, we know that k is some kind of parameter. We know that it's not the variable in question because of the way that our differential is written. So dc dt tells me that c is really that variable of interest. By the way, looking at this, I know that it is autonomous because if c and t are my only variables involved, there are no t's on this side, only c. So this is an autonomous differential equation. For autonomous differential equations, they are separable. So we could be asked to separate this and actually solve for c. But if all I care about is the stability of the equilibria, that we don't have to separate, we don't have to do any integration. We just have to mess with this equation. So to find the equilibria, first of all, we're looking for where is that derivative equal to 0. So if I set this equal to 0, we can see that when c is 4 and c is 10, those are our two equilibria. But we haven't been given a value for k. So if we want to talk about stability, we have two options. We can look at this graphically, or we can do the analytic approach. I'm going to start with graphically. Even though I don't know the value for k, I do know that this is some kind of parabola. And that parabola, if I think about my c-axis and my dc dt axis, this parabola has intercepts at 4 and at 10. As it's written, if I were to multiply this out, I'd end up with a positive c squared term. So that means that if k is positive, then because this has a positive c squared term, if k is positive, my parabola is going to go like that. But when k is negative, my parabola looks like this. So that's really the difference that's going to let us know what's happening to the equilibrium at 10. So let's first try k being greater than 0. So if k is greater than 0, then this is going to come in and look like this. Now thinking about drawing our arrows in here, everywhere that my graph is above the c-axis are places where dc dt is positive, meaning c is getting bigger or I'm moving to the right. And everywhere that my curve is below the c-axis, those are places where dc dt is negative, c is getting smaller, or I'm moving to the left. So we can see here for k greater than 0, 10 is an unstable equilibrium, 4 is the stable equilibrium. But if I draw my graph in with k less than 0, then here's 4 and here's 10. And now my curve should look like this. Okay, I missed. We'll just make it a little bigger. And if we follow that same rule that everywhere above the axis, above that c-axis, dc dt is greater than 0, then I should be headed to the right or towards bigger c values. And everywhere where my curve is below the axis, dc dt is less than 0, and I should be headed to the left. So now my 10 is stable. So the answer is that for k less than 0, 10 is my stable equilibrium. For k greater than 0, 4 would be our stable equilibrium on that problem. Okay. Let's go ahead and do a Euler's method problem. Nope. Let me talk about why that's a bad problem. Or I don't even have to talk about why it's a bad problem, but in general, we're going to apply Euler's method when we couldn't otherwise solve the differential equation. I happen to have just written something that is solvable because it's separable. So actually, let's just solve this one, and then I'll make a new Euler's equation that we couldn't have done this with. So here, the reason that I know that it's separable is I can take that right-hand side and write it as something with x's times something with y's. Now that I've got this as something with x's times something with y's, and I know it's separable, I'm going to rewrite my y prime, get my y's on one side, my x's on the other. When I'm moving my y's to the other side, I'm going to do that by multiplying by the reciprocal of what's here, which means I'll end up with y plus 1 divided by y squared, dy, is equal to 2x dx. So this guy right here, if I'm going to integrate this, I'm going to walk up to it and say, is it algebra, trig, or a mixture of stuff? Well, it's just algebra. So I'm thinking about my algebra trigs. Now, even though it's a fraction, I'm not going to go to partial fractions or long division because I have a single thing in the denominator, which means I can actually write that as two separate fractions. So this can become y over y squared plus 1 over y squared dy. And what's nice about this is both of these are easier for us to work with. So y over y squared, that's secretly 1 over y. And 1 over y squared, I could write as y to the negative 2. There's a reason that I took the first piece and I didn't write that as y to the negative 1 power. This in particular is our special natural log integral. But this guy, y to the negative 2, that's not a natural log. So I'm going to have to be using the power rule on this. So that's why I wrote the two pieces differently. So integrating that, I am looking at natural log of y minus, well, if I add 1 to the exponent, I'll have a negative 1. Dividing by negative 1, that's where I got my minus sign from. And if I add 1 to that exponent, y to the negative 1 is the same as 1 over y. On my right-hand side, if I integrate that, I'll get x squared plus constant. This is an equation that we cannot solve to make it say y equals, but we could make it say x equals if we really wanted to. I could subtract the c over and take the square root, but we'd still have a plus or minus issue when we took the square root to get the x by itself, unless we had an initial condition. And then that could tell us whether we needed the plus side or the minus side. Okay, now that we did that one, let me fix this to what I really meant to write so that it's no longer separable. No questions about this? Okay, now I'm going to look at this, and again, there are only two types of integrals that we know how to actually solve. It's got to be separable or first order linear. Well, it's first order, but it's not linear because of the y squared term, and it's actually not linear because of the 1 over y plus 1 term. So it's definitely not first order linear. This also isn't separable because adding that plus sign means I can't factor this anymore. So we wouldn't be able to solve this even if we wanted to. Instead, perhaps we might be asked to approximate a particular numerical value in this curve, in this solution curve. So if I gave us an initial condition that y of 0 was equal to 1, and I wanted to approximate y of 1 with an h or a delta x of 0.5. So we've talked about this before, but there's two ways that I can specify for a Euler's method problem. I can either give you an h or a delta x value, or I can say, I want you to end up at x equals 1 taking 2 steps. So I'm going to end up at x equals 1 by taking 2 steps, and each step has to be 0.5. I like to get a table going. So right now, I know that we are at an x of 0 and a y of 1. And after I take 1 step, I'm going to be at an x of 0.5. But to figure out the y value I'm going to be at, we need that Euler's equation, which says y sub n plus 1 is equal to y sub n, the place I'm at, plus y prime, or our slope, because the whole idea behind Euler's method is I'm starting somewhere, I'm following the slope for a little bit of distance to get to a new y value. So I'll have y prime times delta x, or h. So to get my new y value, we're currently standing at a y of 1. And now I need to know y prime at the point 0, 1. So if x is 0 and y is 1, that's 0 over 2 plus 1 squared. So that's a 1. And my delta x of 0.5. So my next y value is 1 plus 0.5. So I'd be at 1.5. When I take one more step, I'll be at that x value of 1, which is where we want to end up. And to figure out that y value, I'm going to do this whole thing over again. So now I'm standing at 1.5. I need to know my y prime when I'm at the point 0.5, comma 1.5. So it's not going to be pretty on my y prime, which is why typically on an exam, if you're not allowed a calculator, you're only going to do a couple steps of Euler's method because it gets ugly in a hurry. So for that y prime piece, I'm going to have 2 times 0.5 divided by 1.5 plus 1. So that's 2.5 squared. Oh, I didn't quite leave myself enough space because we're also going to need to add in the 1.5, or the y value I'm currently at, squared, times 0.5. Now, if you happen to have a bunch of time, or if the numbers happen to look real pretty, you could simplify that down. I'm just going to draw an arrow to say that's where it would go, and this is approximately f of 1 or y of 1. I guess I used y in this problem. So let's go with y of 1. So we've got about 15 minutes left. Are there any questions that anybody, any last questions? Anything in particular that somebody wants me to go over? I know this is your time. You're the ones that have to take this final, so I want to make sure it's useful for you. So how about this? Type a 1 in the chat if you want me to keep doing more problems. Type a 0 if you're like, no, that's enough. Okay, I got a couple of 1s. So I'm just going to keep picking problems since you all are still apparently happy with whatever I'm choosing. I have really kind of been focusing on older stuff today, but maybe we should do another eigenvector, eigenvalue kind of problem, or maybe take a look at a determinant for a 3x3 matrix. Oh, weird question in here. My 2.5 squared came from this part in the formula. So the denominator here is y plus 1, and my y value where I'm standing right now is 1.5. So I just did the 1.5 plus 1 in my head to get the 2.5. Okay. So let's have some fun. I'm going to erase this and we are going to explore a Leslie matrix problem. Sure. That looks like maybe it's hard to read, but that's a 3/20. And instead of writing that as 0.25, why don't I write that as 1/4, just to make our lives, just so they're all fractions and I don't have both fractions and decimals. So let's suppose that this is a Leslie matrix that we have been given. First of all, I know that there are 3 age classes in this population because it's a 3x3 matrix. If I look across the top row, and well, actually, let's give names to our 3 age classes. So let's say that I have infants, juveniles. Oh no. Oh, I like 3 weeks ago or something, we were talking, and I said I didn't know what baby sloths were called, so I looked it up. Baby sloths, they're cubs. Let's go with sloths. So these are some sloths, and we've got cubs, juveniles, and adults. Again, I'm going to say the same thing I always say. I'm not a zoologist. I'm not a biologist. I know nothing about the reproductive properties of sloths in the wild. We're just making stuff up. Okay, so we've got this population of sloths, cubs, juveniles, and adults, and this is the Leslie matrix associated with that. So if I look across the top row, this tells me that cubs are not reproductively viable. So each breeding cycle, on average, our cubs have 0 female offspring. Each cycle, our juveniles, on average, have 1 offspring, and our adults have, on average, 3 offspring. This 5/8 tells me that, on average, 5/8 of our cubs grow up to become juveniles. 3/20 of our juveniles grow up to be adults, and 1/4 of our adults survive another cycle. So that's our situation. So let's talk about some things that we might be asked to do here. So let's say that I gave an initial population distribution of so that was my initial population distribution, and I asked you to figure out how many cubs will there be next cycle. I can't spell, apparently. That looks wrong too. I'm going to stop looking at it because I think it's just in my head. Okay, so if I want to know how many cubs there will be in the next cycle, then because this Leslie matrix represents an iterated process, I know that to figure out my N1, that's going to come from taking our Leslie matrix and multiplying it by that population distribution that we were just given. 16, 10, 2. So we're going to practice our matrix multiplication here. I promise I've given us numbers that should work out nicely. So I've got 0 times 16 plus 10 times 1 and 2 times 3. So that's 10 plus 6 plus 0, so 16. Well, that's actually enough to answer our question, because that would tell us how many cubs. There'd be 16 cubs in another cycle, but I'm going to keep going to get these other two values. So to get what's sitting in row 2, column 1, I need row 2 times column 1. So I've got 5/8 times 16. Now I said the numbers worked out nicely. 5 times 16 is 80, and 80 divided by 8 gives me 10. So after one more cycle, I would have 10 juveniles. Now let's check in on our adults. So I'd have 0 times 16 plus 3/20 times 10. So that's 30 over 20. Just write it here. I don't do fractions well in my head. So that's 30 over 20. And then 2 times 1/4. So plus 2/4. Well, 30 over 20 is the same as 3/2. And 2/4 is the same as a half. So that's 4/4 or 2. I know it doesn't seem interesting, but there is something mathematically curious about this. And I can now conclude that one of the eigenvalues of my Leslie matrix must be 1. And the reason I say that is, remember back to, 2 hours ago, our relationship, the AX equals lambda X, that's our fundamental relationship when we're talking about eigenvectors and eigenvalues. Well, what we just saw is that we had a matrix, we multiplied by a vector, and we got a constant times that same vector back. The constant happened to be 1, but this tells me that 16, 10, 2 is in fact an eigenvector. So I could ask you to find, well, so lambda equals 1, that's one of the eigenvectors of this matrix. Well, what are the other eigenvectors? Sorry, that's one of the eigenvalues of this matrix. Well, what are the other eigenvalues for this matrix? I was asked sometime last week to find eigenvalues for a 3x3 matrix. And at that point in time, Didel hadn't talked about cofactor expansion. And so in the context of our textbook, we didn't have a way to find the eigenvalues for anything other than a 2x2 matrix. But now that we know about cofactor expansion, we can find the other eigenvalues of this matrix. So let's go ahead and do it. So I need the space, so I'm going to erase this. So our equation holds no matter what we are working, no matter what size the matrix is. If I'm trying to find the eigenvalues, then I'm looking for the determinant of A minus lambda I to set that equal to 0. Well, A minus lambda I means I'm subtracting lambda from the diagonal. So I'm going to go ahead and take this, and that 0, 0 would be 0 minus lambda, and another 0 minus lambda, and then I'll have 1/4 minus lambda. With our cofactor expansion, I'm always going to want to choose either a row or a column with zeros if I have it to take that determinant. You could also take this determinant the book way of taking this and writing it over here and then writing the determinant out. I'm going to use the cofactor expansion instead. So just to practice it, because the fact that Didel sent that sheet out about cofactor expansion, like right at the end of the quarter, kind of makes me feel like he might expect you to use it somewhere on the final. So let's go ahead and expand across this row. And thinking back to what we talked about on Friday, I know that if I think about my plus minus signs in a grid, this is going to go minus, plus, minus, and then we won't have to worry about the -1 to the rows plus columns. So that 5/8, I'm going to have -5/8 times, and then I'm going to block out both the column that 5/8 is in and the row that 5/8 is in. So if I block out that column and that row, then I'll end up with, oh, this is terrible, but I started down this road. I'm realizing we only have 3 minutes left. I don't really think he'd make you do this with a matrix that had fractions in it. I think he might make you do it for a matrix that had all nice numbers. I don't think he's really going to make you do it with fractions. I'm basically just going to write this out really quickly, but we're not going to finish this off. So I'll have 1 times, I'll have 1/4 minus lambda times 1, and then minus 3 times 3, so 9/20. I'll have a plus, but it's already a minus lambda, so minus lambda. And then if I block that column and that row, then the determinant would be negative lambda times 1/4 minus lambda, and then minus 0, again, because I'm blocking out this row and that column and finding the determinant of the 2 by 2 that's left. And then plus 0. So this isn't pretty, even slightly, but like I said, I think it's possible that he could write a problem where he had whole numbers in there, so that when you did this, what you got was something that you could actually see how to factor it. I think here, this is ridiculous even for Dedel. I put one with too many fractions, sorry. Okay, it's noon. We've been at this for 2 hours. I'm gonna give you one last shot. Does anybody have a last question for me for today? Okay, then the last thing that I am gonna say is tomorrow morning, I will be here in our co-classroom starting at 8 a.m. and I'll be there from, I think I said I'd be in here from 8 to 10 tomorrow. Just doing a quick check, make sure I blocked my calendar off. But yeah, I will be in this Zoom room from 8 to 10 tomorrow morning. If you have any last minute questions, I'm just gonna have it open, and if you wanna pop in and just ask me a quick question, that's totally fine. Otherwise, it's been a totally bizarre quarter, but thanks for hanging in there with me through this not ideal educational situation. I hope that everybody is able to focus enough with everything that's going on right now to be able to concentrate and get ready for this final exam. I hope it goes really well for everybody, and that's going to be it for today.